Welcome to part 2 on the ISA of a simplified DLX. I want to remind you that the instructions in the simplified DLX are all 32 bits long. We have two formats, one called I-type, the other one called R-type. In the I-type, there are three fields: opcode, RS1, RD, immediate. In R-type, there are five fields: opcode, RS1, RS2, RD, and function. Okay, let's start going over the instructions. The most complicated instruction are load and store instruction. These are instructions that deal with copying words between the memory and the GPRs. An informal and abbreviated interpretation of load and store operations or instructions is given in the following table. This is the instruction and this is what it does. Let's go over it very slowly. The instruction is load word. The destination register has an index RD. The address of the index that we want to access in the memory is stored partly in the register RS1 and partly in the immediate field of the instruction itself. So we take the contents of the GPR whose index is RS1, we add to it the constant that is written in the immediate. This addition is a 2's complement addition, in fact, so we actually perform sign extension to the immediate so that it will be 32 bits long, so that we can add it with RS1. This gives us an index. We access the memory in this index. We see what is written there, what is stored there, and we copy the contents of this word into the RD. This is the GPR whose index is given by the 5 bits in the RD field. The stored word just replaces the right-hand side with the left-hand side. So now we store the contents of the GPR whose index is given by RD into the memory word whose index is given by adding the contents of the GPR whose index is RS1 with the constant which is stored in the instruction itself in the immediate field. Let's elaborate on this. Okay, so we notice that we need to compute an address in order to perform a load and a store. We refer to the address in the memory in which we are accessing as the effective address. Now, the effective address in the load or store instruction is defined as follows. We look at RS1. This is the index of the 5-bit index of the GPR that is given in the field RS1 of the instruction. We refer to these 5 bits as encoding a number between 0 and 31 in binary, and we refer to this number as J. So J is the binary number represented by the 5-bit field RS1 in the instruction itself. RJ, this J is the same J as this one. RJ is the contents or the word that is stored in the register of the GPR whose index is J. Now, we take these 32 bits and we refer to them, we interpret them as representing a number in binary. So angular brackets around RJ denotes the binary number represented by the contents of the register whose index is J. This is the general purpose register whose index is J. Now, we take the field immediate. This is a 16-bit field in the instruction itself, and we interpret it as a representation of a number in 2's complement representation. We add these two numbers together, so we add the binary number that is represented by the contents of the GPR RJ with the number represented by the field immediate in 2's complement representation. We perform this addition, and we take this addition and we compute the remainder when we divide this sum by 2 to the power of 32, and this will give us the effective address. This is a very complicated expression for computing the effective address, what I want you to notice is that the immediate field can also represent negative numbers. Therefore, in effect, you could think of this sometimes as subtraction rather than addition. Now, we point out that the event that the sum of the number represented by Rj in binary and the number represented by the immediate in 2's complement need not be a number between 0 and 2 to the power of 32 minus 1. This is one of the possible indices of our memory. Now, if this event occurs that the sum is not representable by 32 bits in binary representation, then this is most likely an indication of a programming error. In certain architectures, such an event creates what is called a segmentation fault, which immediately stops the execution of your program. In the simplified DLX, we do not consider this event to be an error, and the modulo operation is a side effect of using a simple adder for computing the effective address. So we really do not care whether this number is too big or negative. We just take the remainder, mod 2 to the power of 32. This will always be a number between 0 and 2 to the power of 32 minus 1, and this will be our effective address. So we can never go wrong. Of course, it might be useless to access this address and read or write into it. Maybe even will lead the system to do some errors, but this is the problem of the programmer in the simplified DLX architecture. Of course, if you were to design a real architecture, then you would like to have some measures for detecting such events, which are most likely an error, because reasonable programming should not lead to a computation of an effective address which is too big or too small. Now, the semantics of a load and a store instruction are as follows. Let I be the index, the index of the GPR that is encoded by the RDE. This is 5 bits in the instruction in binary. Okay? And RI is the GPR whose index is I. So now what a load instruction does is it takes the effective address, it accesses the memory word whose address is EA, copies its content into the general purpose register RI. Okay? What a store instruction does is you just flip the left hand side and the right hand side, right? So now you take the contents of the register RI, this is a general purpose register, and you copy it into the word in the memory whose address is given by the effective address. These are the semantics of load and store instructions. We will elaborate on the notation that we used for load and store for other instructions. So as before, RI denotes the word stored in the register in the GPR, whose index is given by the field RD in binary representation. RJ1 is the contents of the general purpose register, whose index is given in binary by the field RS1 in the instruction, and RJ2 similarly is the contents of the register in the GPR, whose index is given by the 5-bit field RS2 in binary. And again, RS1, RS2, and RD all appear explicitly in the instruction itself. Okay, so let's talk about an add instruction, which is an I-type instruction. It is called add I. It has 2 arguments, RS1 and immediate, and 1 destination, RD. And what you do in this instruction, you simply add the contents of the register RJ1 with your immediate, which is a constant that appears in the instruction itself. This addition is a 2's complement addition, but after you've performed this addition, you compute the mod with 2 to the power of 32. And then you look at the binary number. This is a very strange way of just saying I feed RJ1 and the immediate, after I perform sign extension to it to extend it to 32 bits into a regular binary adder. Okay, so this is my binary adder. Just a very strange way of saying the following. Here I input RJ1, and here I input the sign extension to 32 bits of the field immediate. So this is 32 bits, this is 32 bits. The carry in is always a 0 here because it's an add, so the carry in is a 0. And I take the output, 32 bits. I don't care about the carry, not connected. And this will be what I store in RD. Okay, this is the way it's implemented in hardware. And of course, the semantics are given in this line, but quite hard to follow. Okay, good. The shift instruction are R-type. So here we are ignoring the second operand. We only have a single operand. And we either do a logical shift to the left or a logical shift to the right. So this one is a left shift, and this one is a right shift. This is the meaning of this L and the R over here. What you do is you take the contents of RS1 and you shift it to the left by 1 position, store the result in RD. Take the contents of RS1, shift it by 1 position to the right, store the contents in RD. These are the two shift instructions, which happen to be R-type instructions. We have additional R-type instructions like addition, subtraction, bitwise AND, bitwise OR, bitwise XOR. In all of these instructions, I have two operands given by RS1 and RS2, and I either perform addition, subtraction, bitwise AND, bitwise OR, bitwise XOR on these two operands and store the result in RD. And in the case of addition and subtraction, these are the semantics. We already saw them. Notice that in the case of subtraction, the actual computation we're doing is a minus, not a plus. That means that our adder that we showed before, this is our, this is the adder I drew before. So it will be given RJ1 and the sign extension of the immediate to 32 bits because the immediate originally is only 16 bits. And now in a subtraction, I have to input a 1 here to perform the, sorry, I'm wrong here. This is wrong. In a subtraction, I take the bits of RJ1 and I negate them. So this is the way this subtraction takes place. Okay, you could also write the semantics like this. Will give you an equivalent expression. Very good. We have instructions which are called test instructions. These are instructions that compare two numbers in 2's complement representation. The first one is the number that is stored in RJ1, and the second one is the number that is given in the immediate field of the I-type instruction. And we want to compare these two numbers, and the result of the comparison is stored in RI. So for example, if we want to do a comparison of less than, this is less than, then we check whether the number represented by RJ1 is less than the immediate. If this is the case, we store a 1 in RI, otherwise we store a 0. Now, in fact, this 1, I just want to emphasize, do not be confused. This 1 is actually 0 to the power of 31 concatenated with the 1, and this 0 is actually 0 to the power of 32 as a string. Okay? This is the string, and this is the string. And this is the value that is represented by the all zero string, the value that is represented by this string. Very good. We have 6 types of test instructions, all of which are in I-type. We have less than, equality, greater than, less than or equal, greater than or equal, or not equal. And depending on what the instruction is, if the condition is satisfied, we store in RD1. If the condition is not satisfied, we store in RD0. Okay. In all cases, we compare the contents of RS1 with the value of the immediate. All of this comparison takes place in 2's complement representation. Okay, so this is with respect to 2's complement representation. Okay. Branch and jump instructions are I-type instructions that modify the value that is stored in the PC in a non-standard fashion. So, during the execution of every instruction, the PC is incremented. So the normal state of affairs when you execute a program is that you have instruction 1, and then the next instruction you store is the next instruction in memory, and the instruction that you run afterwards is the next instruction in memory, and so on and so forth. So this would be the first instruction, this would be the second instruction, and so on. Okay, they are stored in memory. This is memory in a contiguous way, one after the other in the memory. Okay. Now, when you want your program not to execute instructions one after the other as they are stored in the memory, you may want to have a situation in which your instructions, let's try to explain how things are being executed. Let's say you have a loop and you want to execute the first instruction, the second instruction, and now after you go to here, you want to come back to here. This is not a great idea what I'm drawing, because this would be an endless loop, right? But let's see if we can do something like this. We want to jump from this instruction to here. So what I want to emphasize is the default situation, default situation. PC gets the value of PC plus 1. That means the next instruction you want to execute is stored in the next word in the memory. This is the default situation. And here we have a deviation from the default situation. This is a deviation from the default situation where we're not going to the next instruction. Okay, I want to emphasize, we are not going to the next instruction. Instead, we are jumping to some other instruction. This is called a jump instruction, and I'll explain what a branch instruction is shortly. Okay, so let's explain. Branch and jump instructions modify the value stored in the PC, because the default update of the PC when you execute an instruction is to increment the PC so that the next instruction you execute is the one that appears after it in the memory. In a branch or jump instruction, an additional change is made to the PC. So what I mean by additional is, since the default is to do PC gets the value of PC plus 1, now I'll do something like PC gets the value of PC plus 1 plus another thing. Let's call it the jump for the time being. Okay? This is the default value of the jump is a 0, but in branch and jump instructions, we may jump to an instruction which is not the next instruction. Okay, the simplest instruction in this set of branch and jump instructions, which are all I-type, is jump register. Jump register means change the PC so that PC gets the value of RJ1. This is the simplest form of a jump. You store the next instruction, the address of the next instruction that you want to execute in RJ1, and you simply set PC to be equal to RJ1, and you jump to that instruction. That will be the next instruction that you execute. Okay, so the next instruction is stored in the memory location M with the address RJ1, because RJ1 is the next value of our PC. A somewhat more evolved form of disrupting the normal sequence of instructions that are being executed is the jump and link register. This is a really interesting jump. Here, what we do is we store the next instruction that we were supposed to execute under normal circumstances in R31, and then we jump to the location given by RJ1. Why would we want to have such an instruction? So suppose I have instruction 1, instruction 2, and now I have instruction 3, which is a procedure call. I want to execute some procedure with some parameters x, y, z, it doesn't matter. And then I have instruction 4. So how is this program actually executed, right? So I execute instruction number 1, then I execute instruction number 2. What does instruction number 3 tell me? Instruction number 3 tells me, oh, I want to perform a jump to where the procedure is with, say, some parameters. It's not important now. So here's my procedure. So now I jump to my procedure. I execute my procedure. Once I reach the end of my procedure, what should I do? What is the next instruction that I should execute? The next instruction that I should execute is instruction number 4, because this procedure was called by instruction number 3. Once I finish running the procedure, I'm supposed to go back to instruction number 4. But this procedure in itself does not know where to return to, because it might be called in different places in my program. So to save the return address, what I do is I employ R31. I store in R31 the next instruction to be executed, because when I was in instruction 3, I wanted to jump to the location of the procedure, which is stored in RJ1, but I have to somewhere write where I'm supposed to return to. So this is a place I'm supposed to return to. I execute the procedure. The procedure makes sure that it doesn't contaminate R31. If in case it does, it needs to store it in the side and then reconstruct it. I won't get into that detail. Let's assume that my procedure is written in a very meticulous way that it doesn't modify the value of R31, and then it go back by setting the PC to R31. This is how this return from the procedure can be implemented. And this is why it's called jump and link, because it gives us the way to jump back to the next instruction. Good. We also have 2 branch instructions. One is called branch equals 0. The other one is called branch not equals 0. Okay, so this is branch if 0, branch if not is 0. They are denoted by branch equals 0, branch not equals 0. In the branch equals 0 instruction, we do the following. We compare the contents of the general purpose register RJ1 with the all 0 string. If we have equality, then a branch takes place, and the address of the next instruction is going to be PC plus 1 plus the value represented by the immediate field in 2's complement representation. Recall, we're talking about an I-type instruction, so it has an immediate field. This immediate field determines the jump amount. If RJ1 does not equal 0, the all 0 string, we're talking now about a branch equals 0 instruction. If it doesn't equal the all 0 string, then branch is not taken, and the address of the next instruction is PC plus 1. So the situation when we have a branch equals 0 instruction, it will have our RS1, and it will have our immediate. So this is the instruction we're looking at. You compare this is your current instruction. So this is the current instruction. You compare. If RS1 does not equal 0, then this will be the next instruction. However, if RS1, let me do it differently. If RS1 equals 0, then this is a plus 1, right? Now we will have a plus 1 plus immediate. And this will be the next instruction that we're executing. Okay? Now, I want to emphasize that the immediate could also be negative. It need not be a positive number. It could also be a negative number, in which case the jump takes us back rather than forward. This is how, for example, a loop could be implemented. We'll see this shortly. Okay. In a branch not equals 0 instruction, the conditions are reversed. You take the branch if rj1 does not equal 0, and you do not take the branch if rj1 equals 0. Okay, let's summarize. We have 4 branch or jump instructions. All of them are I-type. Branch equals 0, RS1 immediate. Branch not equals 0, RS1 immediate. Jump register, RS1. Jump and link register, RS1. The semantics are as follows. In jump register, RS1, you simply set the PC to be equal to RS1, and the next instruction you're going to execute is the instruction whose address is stored in the general purpose register whose index is RS1. Jump and link registers first saves the next PC in the next instruction in R31, and then updates PC to perform a jump to a procedure. Branch equals 0, we have 2 conditions. Either RS1 is 0 or RS1 is not 0. If RS1 is 0, we jump to the address PC plus 1 plus the contents of the, plus the number represented by the immediate in the instruction itself. If RS1 is not 0, we just continue with the next instruction. In branch not equals 0, these 2 conditions are swapped. We have 2 more interesting instructions. The first, they're both I-type. The first one is a no operation. It's a NOP. It's just doesn't do anything. It has no effect, and the only thing that happens during this execution is that you increment the PC to go to the next instruction. So it's an instruction that doesn't do anything except for waste time. And then the PC goes over it and skips to the next instruction. The second instruction is the halt instruction. This is an instruction that causes the microprocessor to freeze and stop the execution. Okay, that's the end of the story once you reach a halt instruction. This is a partial table of all the I-type instructions. You see the load word, store word, add I, test and set operations that do a comparison, and the result of the comparison is stored in RD. Control operations, jump and branch, and then we find that we have the NOP and the halt. Okay. Now you see that the 6 most significant bits of the instruction register tell us which operation, which instruction we're executing. This is what is called the opcode, and this is the opcode field in the instruction. R-type instructions, we have shift operations by shift left or shift right by 1 position, and we have the arithmetic and logical operations of addition, subtraction, and or and XOR. These are our R-type instructions. Notice that in all these instructions, the opcode is all zeros, 6 bits of zeros, and you can tell which instruction you're actually doing by looking at the function field, which is 6 bits, the 6 least significant bits of the instruction. Okay, they tell us whether we're doing a shift to the left, a shift to the right, etc. Okay, let's see the power of the ISA. Let's look at a short segment of a program written in C and see if we can execute such a segment using DLX instructions. So what do we have here? We have here variables. So let's just list them. We have the variables I, J, F, G, and H. And we have certain operations like addition, subtraction, comparison. We have, well, this is terrible coding, but we have here a jump, which says, well, if we have equality, jump to this instruction and skip over this instruction. Okay, so we understand what this program segment does. The first thing we want to say is well, we have these 5 variables. Which register is assigned to each variable? And of course, had we had more than 32 variables, we would have had a problem. We would have run out of general purpose registers. But in this case, we don't have so many registers. Sorry, we don't have so many variables, so we do not have a problem. We simply store F in R1, G in R2, and so on. Good. So we have determined what is the register assignment, namely which variable is mapped to which general purpose register. Now we want to run our program. This is our C code. And we want to compare I with J. So we notice that I is stored in R4 and J is stored in R5. And we want to compare R4 with R5. Okay. How do we compare R4? So this is I and this is J. Let me just emphasize this point so that we won't forget. This is I and this is J. How do we compare I with J? Well, one way to compare I with J is to perform a bitwise XOR of I and J and store the result of the bitwise XOR in R6. So we know that R6 is going to be all zeros if and only if I equals J, right? Because we're doing bitwise XOR. Okay. Now, what we can do, we can implement this branching by comparing R6 with 0. Now, if R6 is all zeros, then I equals J, and we want to jump to L1. So we'll perform a branch. Let's leave the branch amount as a riddle. We have yet to understand why this is a 1. Okay, we will establish this in a second. Now, in this line, we want to perform addition. F equals G plus H. So G and H and F are stored, G and H are stored in R2, R3, and F is stored in R1. So this is actually F. And this is G and this is H. So what we're doing is we're adding G with H and storing their sum in F. This is what we're doing. This is what we wanted to do. So R1, now, as a result of this, R1 actually has the value of G plus H. Good. Now, in this line, we wanted to do F equals F minus I. So we want to subtract I from F. So this R1 is F, R4 is I, R1 is F, so we do subtraction, F minus I, and the result is stored in F itself. Look here, the RD and RS1 can be the same register. There's no mistake over here, right? So this does R1 gets the value of R1 minus R4, which is actually F gets the value of F minus I. Good. Now we're left with the issue of this jumping. We wanted to skip over this instruction in case R6 is all zeros. Now the default is PC gets the value of PC plus 1. And when the R6 indeed equals 0, then you skip by the amount which is given by the immediate. This is this immediate. We're focusing here on this immediate now. Good. So we want to go from this instruction to this instruction. So by how much should we increase the PC? So the PC is already incremented by 1. We want to skip plus 2. So this value should be 1, and this is why the 1 appears over here. Okay, very good. So we were able to encode this C code segment using these 4 instructions in DLX's machine code. Let's see another example. In this example, we have an array, A, and we have a loop, which updates the value of G to be G plus AI, and now I is you add J to I, you update I, If I is not equal to h, then you go to the loop. Otherwise, you get out of the loop. Okay. So one issue that we want to understand here and recall that the implementation of an array in C is that you have A0, A1, and so on, and the address of A0 is just the address of A, the address of A1 is the address of A plus 1, and this would be the address of A plus 2, and so on and so forth. So the entries of the array are stored in memory one after the other. The first one is stored in a location which is pointed to by A, and then there is the location which is pointed to by A plus 1, and so on and so forth. Okay? Good. So, A, this is the beginning of our register. A points to A0. Yes? We will use R5 for that. We will use A plus I, we will store that in R6. So this will be, if this is AI, then this will be A plus I. The contents of AI will be stored in R7. So the actual contents that we have over here will be stored in R7. And the result of comparing I with H, checking whether they're not equal, is stored in R8. And we have the variables G, which is R1, H in R2, I in R3, and J in R4. Okay? So I just want to emphasize, maybe I confused you here with the address. Maybe I don't need this ampersand, yeah? So A points to the beginning of the array, okay? I think this is wrong in C, I'm not sure. Good. How do we do the encoding? Okay, so let's copy the table shortly so that we have it in front of our eyes. GHIJ, we have GHIJ. These are registers R1 to R4, R1, R2, R3, R4. And we also have A plus I, AI, and I not equal to A. That would be A plus I, AI, I not equal to J. Sorry, it's not J, it is I not equal to H. Let's fix that. I not equal to H. And this is R5, R6, R7, R8. Okay, so I just copy the table so that it will be handy. Good. Okay, so now let's try to do the translation. First thing, we need to find out what AI is. Okay, for that purpose, we need to add A with I. Now, A is R5. And I is R3. So we add A plus I, and we store the result of A plus I in R6. This makes sense. So this is this one. So this does AI, R6, sorry. R6 gets the value of A plus I, just so that we see that. Now we want to load into R7, we want to load the value of AI. So the value of AI will be given by the contents of the register A plus I. This gives us the address, and the immediate will be 0, because this is the entry we want. We don't want any other entry, and we want to store that in R7. So now R7 gets the value of AI, and this is what we wanted. So R7 is ready. Now we can finally perform the addition of G plus AI. So R1 is G, this is G, and this is R7 is just AI. So now R1 is just G plus AI. And we finally completed this execution of this instruction. We're very happy. Good. Now we want to add I plus J into I. I is R3, J is R4, so we do add R3, R3, R4. We already saw an instruction of this form. And now we want to compare whether I does not equal H. So one way of comparing whether I is not equal to H, we do a bitwise XOR of I and H. I is R3, H is R2, so we do a bitwise XOR of R3 and R2, and we store the result of this bitwise XOR in R8. Now R8 will not be equal to 0 if and only if I does not equal 0. So now we do branch not equal 0, depending on R8. And now we have to determine by how much we jump, because we want to loop. We want to loop from here back to here, right? Good. So we want to go back from this instruction back to this instruction, okay? Now, this was my PC, and this is the destination PC, right? What is the difference? It's -1, -2, -3, -4, -5. But I know that the jump will be PC plus 1 plus what is given by the immediate. And I want this to be -5. So in order for this to be equal to -5, the immediate has to be -6. And this explains the 6 that you see over here. Very good. Let's summarize. In this chapter, we described the ISA of the simplified DLX. Even though the ISA is rather simple, we see that C instructions and programs can be translated to the DLX machine language. Missing in this description is the support of system calls, distinguishing between protected mode and user mode, etc. All kinds of features that a full-fledged microprocessor must have. Thank you very much.